So I'm going to do a problem where you are given the pH of a certain concentration of a solution of a weak acid, and you're asked to calculate the pKa of that acid. So in this case I have lactic acid, and I'm not even given a formula for this acid, but that's okay. All I have to know is that it's a monoprotic acid, which it tells me in the problem. So since pKa is related to a Ka value, and K is representing equilibrium concentrations, we need to write an equilibrium reaction for this acid. And we can just use, since we don't know the structure of it, we can just use the generic HA. And A happens to be the rest of the molecule that we don't care about, and H is the H that comes off. Okay, I'm going to write it, well, I guess I'll write it with the water in there, so that one of my products is a hydronium. Okay, so this is the equilibrium. If I didn't write the water as a reactant, then I could just use this equilibrium reaction here, like this. And you'll see that either reaction will give you a just fine ice table to work with. So we're going to, because this is an equilibrium concentrations problem, ultimately, we're going to use an ice table. So let's set that up. Okay. So we are told that we have a 0.025 molar solution of lactic acid. That means that if we were to make this solution, we would weigh out enough moles of this pure HA here to put in enough water to make this molarity of solution. So we can think about this 0.25 as the initial concentration of our HA. It does dissociate, but when I say 0.025 molar solution, I'm saying that that's my concentration calculated for HA. Okay? And so we can make that assumption, and we can make the assumption that since that's our initial concentration, when we're pouring it into our solution, adding it to water, at first we have no hydronium or conjugate base of this acid. Then we're going to get a change, and then we're going to finally come to equilibrium. So we're going to produce some H3O+. Before I jump to the change row, right away I'm going to look at the equilibrium row, because I have this information here. I have the pH value, and that's the pH value at equilibrium in this aqueous solution. And that is enough information to tell me how much hydronium ion that I have in this solution. I have 10 to the negative 2.75 molar hydronium. And since I have just as much conjugate base as hydronium, we're going to disregard the autoionization of water in this, which contributes a little more H3O+. But we're going to treat this as though all of the H3O+ is coming from HA, adding to the water that's already there. So that means that we have an equal amount of A-, 10 to the minus 2.75 molar. Okay, and that means that we have added this amount, so we can put that in the change row. To 0, and we've subtracted it from our initial concentration of HA, because it's a 1-to-1 stoichiometry. Okay, so we're effectively subtracting this 10 to the negative 2.75 from our 0.025 initial concentration. And why am I ignoring water? Well, it'll be more obvious if I put the phase label there. It's a liquid, it's a pure liquid, and so it doesn't enter into my K value at all. So I don't need a value for water, which is why using this equation up here will work just as well for you as the equation that I wrote. I just wrote the equation adding water to be a little bit more physically accurate. So now I have enough information to write, to calculate my Ka. So my Ka is equal to my concentrations of my products raised to their stoichiometric values, which are 1 over the concentration of my reactant. And again, I'm leaving water out because it's a pure liquid. Okay. So what this means for us is that for my concentrations of hydronium and weak base, I have the same value, so I can just square that. So I can say 10 to the minus 2.75 molar squared. And I can put that over my 0.025 molar minus 10 to the negative 2.75 molar. Okay, so I have all numbers in there. I now have enough information to calculate what my Ka is. That ends up being 1.36 times 10 to the negative 4th. And remember, our Ks don't have units. And then all I have to do is take the negative log of that to get my pKa. And that ends up equaling 3.87. Okay, so the pKa is below 7, meaning it acts as a weak acid, which is consistent with what we know about this. It's lactic acid. It's named as an acid. Okay. Another thing that we can do with this, now that we know we have our ice table and everything like that, is we can determine the percent deprotonation, which can sometimes be useful when you're thinking about an acid. To what extent does that proton come off? And all we have to do for this one is just take the concentration of our H plus that has come off, and I'm writing it as H plus just to illustrate this a little bit more clearly. You can also put H3O plus, of course, over the initial concentration of my acid. Okay, so this is the equilibrium value of H plus, and then my initial concentration of HA. Multiply that by 100 to give it a percentage value. And so this equals, in our case, 10 to the negative 2.75 molar over our initial concentration of 0.025 molar times 100. Okay, so if I do that calculation, I end up getting 7.1%. Okay, so those are the kinds of things that you can do with pH information. Just think about this as not being so different from the other ice table problems you've done when we were just talking about equilibria in general. It still follows the same rule as other equilibria. You can still use an ice table. You just might need to fill out different portions of that ice table than you're used to.